Every single second, your eyes, ears, and peripheral nerves bombard your brain with gigabytes of raw sensory data. But when you want to respond, to type a sentence, manipulate a tool, or speak a thought, you are forced to squeeze that immense cognitive processing through a tiny biological funnel, your fingers and your vocal cords. This diagram maps the input-output bottleneck. Left, massive sensory input bandwidth. Right, motor output restricted to a trickle of 10 to 100 bits per second. To keep pace with AI, Nuralink concluded we must bypass peripheral mechanisms entirely, extracting data straight from the cortex. Non-invasive wearables like EEG headbands cannot physically capture high-resolution signals through the thick, insulating bone of the human skull. To achieve meaningful bandwidth, the interface has to be invasive. Today, we are going to deconstruct the hardware and software architecture of the Nuralink N1 implant to see how it overcomes the historical failures of direct cortical technology. Overcoming this bottleneck effectively transforms human-AI symbiosis into a challenge of materials and mechanical engineering. The greatest obstacle to recording neural data is that the human brain is not a static object. Suspended in fluid, cortical tissue constantly shifts and pulses in rhythm with every heartbeat and respiratory cycle. For decades, the academic standard has been the Blackrock Utah array, a rigid matrix of thick silicon needles. This creates a severe mechanical mismatch. The silicon scrapes the naturally shifting cortex, generating friction that triggers an immune response, building dense scar tissue around the needles. Over time, this scar tissue acts as an electrical insulator, progressively deafening the electrodes until the neural signal is lost completely. Beyond signal degradation, legacy systems suffer from a secondary architectural flaw. They require a percutaneous pedestal. This means a metal connector must permanently protrude through the patient's scalp to link the internal array to computers, introducing severe infection risks. Until an implant can mechanically mimic the physical properties of the brain while operating entirely internally, long-term high-bandwidth data extraction is biologically impossible. To solve this mismatch, Neuralink abandoned rigid silicon. This breakdown of the N1 implant reveals their primary hardware innovation: 64 incredibly flexible threads extending from the processor. Made from a biocompatible polymer, they measure 4 to 6 micrometers across, roughly 1/10 the thickness of a human hair. Because they lack structural stiffness, these threads float harmlessly in tandem with the cortex's natural micromovements. They yield to the shifting tissue, mitigating shear stress and preventing glial scarring. Despite their microscopic size, these flexible threads house a total of 1,024 electrodes. These nodes feed directly into a custom integrated circuit, creating a 1,536-channel recording system. All of this processing power is packed into a coin-sized enclosure designed to replace a small portion of the skull, sitting perfectly flush with the surrounding bone. By integrating an onboard battery and inductive charging capabilities, the N1 completely eliminates the need for a protruding pedestal. The skin is closed entirely. The N1 solves the biological mismatch by hiding massive, high-density data processing within a cosmetically invisible, biomechanically compliant package. The same polyamide threads that allow the implant to survive are physically impossible for a human neurosurgeon to handle. Their extreme flexibility means they cannot be manually guided. The N1 architecture is therefore entirely dependent on its deployment mechanism, the R1 surgical robot, which uses a microscopic needle to precisely grasp and insert each thread. The main insertion risk is striking a blood vessel. This optical view reveals the brain's dense vascular network and tiny green safe zones. The R1 uses real-time imaging to recalculate its trajectory, executing a vessel avoidance protocol to strike exclusively within those safe zones. Operating at this scale, the robot achieves an insertion speed of 1.5 seconds per thread, reaching depths that safely accommodate 99% of human anatomical variants. Achieving a high-density, flexible neural array is entirely dependent on automated, high-speed robotic precision. In 2024, this highly automated, flexible architecture faced its first real-world stress test. The FDA authorized the PRIME study, a clinical trial targeting severe quadriplegia. The Pioneer cohort established an immediate baseline of success. Within their first weeks, participants achieved information transfer rates exceeding 10 bits per second, controlling a digital cursor at comparable speeds to an able-bodied person. But roughly 1 month into the trial, the hardware failed. As this graph shows, the system's performance plummeted sharply. The brain's natural pulsations caused several flexible threads to physically retract from the tissue, drastically reducing the number of active recording electrodes. Faced with degraded hardware, Nuralink engineers pivoted. They modified the decoding algorithm to become hypersensitive to low-amplitude signals from the surviving electrodes. This software adjustment successfully restored the participants' cursor speed without requiring physical intervention. With the system stabilized, subsequent participants reached advanced vocational milestones. Patient Alex utilized CAD software for 3D design, while another patient, Brad, achieved AI-synthesized speech restoration. The PRIME study demonstrated that the commercial viability of brain-computer interfaces relies heavily on software resilience, compensating for the inevitable physical degradation of biological hardware. The neurotechnology landscape is defined by a strict engineering trade-off. We map this comparing surgical invasiveness against data bandwidth. In the bottom left, we plot Synchron's stentrode, leading in minimal invasiveness by traveling directly through the jugular vein. While routing through blood vessels entirely avoids a craniotomy, it restricts the device to roughly 16 channels. This is sufficient for basic digital clicking, but lacks the bandwidth required for fluid speech or complex 3D design. Nuralink sits in the opposite quadrant. They accepted high initial surgical risk to secure maximum data throughput, establishing 1,024 channels. But their 2026 scaling strategy aggressively pulls that invasiveness score down by developing a dura-piercing technique. By programming the R1 robot to thread electrodes directly through the dura mater without physically removing the protective membrane, they drastically reduce surgery duration. This automation is a strategic necessity to move the procedure out of specialized operating rooms and into outpatient clinics, establishing a rapid, LASIK-like standard of care. Concurrently, the company is preparing a next-generation 3X implant, targeting significantly higher electrode densities, providing the throughput required to execute complex telekinesis across multiple digital and physical environments in real time. By fully automating neurosurgery, Nuralink is positioning human-AI integration as a standardized, mass-manufactured medical reality for tomorrow.